Hello everyone. Today we will talk about regression analysis. Okay, and regression is something that you do quite regularly as an engineer. So the idea here is that you want to measure how you want to understand how a measured value, right, changes in respect to an independent variable. Okay. Let's make an example. Let's say you have a coupon specimen, right? You're testing with your instrument machine, right? You're applying force, pretty good. And then obviously this, has a measured stiffness, right? You're say measuring a force, a displacement curve, right? And you're trying to understand how the stiffness, right? In this case, this is your measured value, right? Changing with, say, thickness of the sample, right? And in that case, that will be the independent value, right? For example, if this is like, let's say, a linear relationship, right, like that, for a thicker sample, right, you'll obviously expect that this to be a larger force for the same displacement because you need more force and so on and so forth, right? So you want to understand how then the slope of your curve, right, for example, is changing, or how this relationship is changing, right? And obviously, in analysis, you won't be able to get all of those points, right? So you can only get some. Let's say you measured like 8 samples or so, but from that, you want to sort of estimate a bigger range, right? Or how in between the thicknesses that you've chosen, how that regression will change, right? So to do that, we will do something called a regression analysis, and then the most common version of that is that the least square regression analysis, okay? So the least square regression analysis. Okay, so to do that, you basically fit a polynomial, right, to your function, right, and you'll define the relationship. Let's say our relationship, for example, let's say this was the stiffness versus thickness, right, of a coupon specimen, but it could be anything really. Here, x1, x2, x3, these are, say, your 2 and 3 thickness values that you measured, right? And then this was the relationship, right? Let's say for each one of these, right, that corresponded to a certain stiffness value, right, then you will say that this will be y bar, right, which is a function of x1 bar. This is y2 bar, right? It's going to be a function of x2 bar, and that's going to be y3 bar, which is a function of x3 bar. Okay, and then the idea here is that the function y bar here, right, is a function of fx bar, right? And you can make number of measurements, right? You can make number of measurements, right, to estimate your polynomial, right, with a highest order of m. In that case, m is smaller, right, or equal to n minus 1. So what this means is that if you measured only 2 points, let's say x1 and x2, right, in that case you'll have 2 points, right, then your polynomial gonna have to be first order, right, because you have 2 points, you can only draw a line between the two. If you have 3 x points, right, then your points polynomial can be second order. That means that you have 3 points, right, and then you can fit a sort of a second order line to that polynomial, and so on and so forth. For these type of things, the rule of thumb, however, is not to select the highest order polynomial, right? So if you know that the relationship between thickness and the stiffness is linear, you can still use a first order polynomial, or if you know that this is a second order relationship, you can still fit a second order polynomial, depending on the physics of the problem that you're working with. Usually fitting a maximum order of polynomial that is available to you is not going to give you a good answer. You should follow what you think the relationship follows, like maybe a logarithmic relationship, second order, third order, so something like that. Okay, so let's define a couple of things that will help us to do this regression analysis. Okay, so I want to call the yi, right? So that's the measured value, right, based on the xi that I used. Yc is that the polynomial, right, I use to estimate yi at xi point. Okay, it will become sort of clear as we are doing it. And then difference is that the difference between delta between yi and yc at each xi point. Okay, so in other words, I can define d, okay, as the sum of all the points, right, starting from 1 to n, right, the difference between yi minus yc squared, okay, and then the yc is going to be an m order polynomial, so that means that's going to be a0 plus a1x plus a2x squared, right, and then it goes all the way plus amxm, okay, and then the d, the difference can be then rewritten based on these, right, as d equal to, right, I equal 1 to n yi minus, right, a0 plus a1x plus all the way amxm squared. Correct? Okay, so what we want to do is that we want to minimize the difference. Okay, and if you want to minimize a polynomial or minimize an expression, right, what you do is that you do set the differential of this to 0, right? So then you can find the terms that will satisfy that relationship. To do that, we can define the differential of d, right, as partial d partial a0 times d a0 plus partial d a1 dA1 and all the way to partial d partial am times dAm. Okay, and to do that we can set all these ones 0 one by one, right? To do that, to minimize the difference, right, we can basically write these definitions here, right? D a0, right? A0 is going to be I equal 1 to n yi minus a0 plus a1xn plus amxm, right, equal to 0. That's going to be square, close it that way. That'll be equal to 0. We can do the same for partial 1, right, dA1. Okay, that'll be again the same thing. That will be I equal 1 to n yi, right, minus a0 plus a1x plus all the way to am times xm squared, and that's going to be 0. And you can do this for all the terms basically, right? The AM is going to be the AM, right? It's going to be that. I equal 1 to n, yi minus a0 plus ia max m plus am times x over m squared, right? And that's going to be 0, so on and so forth, right? So in each time you're going to take the derivative with a1. For example, in this time, this is going to go away, right? In this one, everything but this term is going to go away, so on and so forth, right? And then you'll get the set of equations, right, based on the order of the polynomial, and then you are going to solve for a0 all the way to the am, right? So you don't do that by hand in reality, right? What you do is that you do it either in Excel, okay? In Excel, this is called a trend line. We'll do that today. Okay, and in MATLAB, you can use this to do least square regression. And that will do that job for you, okay? So once you have determined all A0 and AM, right, your standard deviation can be defined as, right, the standard deviation of your yx curve, right? So that's a little bit different than the standard deviation that we've been using so far. It's going to be I equal 1 to n, right? yi minus yc squared, right? Divided by the degrees of freedom, right? Square root. And in this case, you can imagine that this is the top term is actually your d, right? So this term is actually equal to d, right, as we defined it. And then your degrees of freedom is going to be n minus, okay, minus m plus 1, okay? And then the n here is the number of xy points in your graph, okay? So then the confidence interval can be defined as, okay, yc, okay, which is the polynomial value at point x, right, plus minus a t value with certain degrees of freedom, which is this degrees of freedom here, right, times the xyx, right, which is your standard deviation, divided by square root of n, okay? And then from here, a certain p-value, and obviously that p-value determines that the p-value for your t number that you're going to select, okay? So, so basically, this tells you how what is the confidence interval that you think, right? That your polynomial defines the real curve that you got experimentally within this uncertainty, right? Okay. And also, there's also R square value that I want you to sort of understand. The R square value is commonly used, right, to understand how good of a fit that the YC is for YI values, right, that you got. And if R square is equal to plus minus 1, you have a perfect fit, okay? If it's like 0.9, you have reliable fit, okay? If it's between 0.6 and 0.9, you have low confidence fit, okay? And if it's like less than 0.6, that means that very low confidence or no fit, not a good fit. Okay, you can check the notes that I'm going to post on how to calculate R-square, because you really don't calculate it in any of the techniques that we are going to use in both MATLAB or in Excel. Okay, so so for example, let's do example, and then we'll do this in Excel, and I think you can see part of that on the left side. You've been wondering what that example is. Let's say we measured a number, right? Let's say this is LVDT, right? And then LVDT, we have X values measured in centimeters, right? Those were 1, 2, 3, 4, and 5 centimeters, right? Let's say you had an LVDT, right? And LVDT can be something like that, and basically you can move that LVDT left and right, and based on that extension L, right, it will give you basically a voltage output, right? So it's commonly used in instrument machine testing, so you can understand what the force displacement curve is, right? So that displacement, that force, that displacement comes from LVDT, right? And then you have probably a force sensor as well, and that will give you the force, right? So that will be two sensors. Okay, and then out of that, right, you get volts. Y output is in volts. Okay, and then it was 1.2, 1.9, 3.2, 4.1, and 5.3. Okay, the question here is that the YC, okay, what is YC, okay, and also find the standard deviation YXY, SXYX, I'm sorry, and then R square, and also your confidence interval. Okay, and then it also says the XY relationship, right, is linear. Okay, so that means that we are going to use a first order polynomial, right? Even though we had 1, 2, 3, 4, 5 x values, right? You can have to go to fourth order polynomial, but since this is a linear relationship, that means that you will do a linear curve. Okay, so I'm just going to switch over to Excel now. And as you can see here, Excel is on this side. So let me walk through the whole process. So here's your X values. These are Y values, okay? And then here's the polynomial value. Okay. So how I'm going to get my polynomial value? Okay, so let's go to an example, part of the example that it was not, done yet. What we'll do is that we have 5 points of xy, so that means that's n, that's 5, okay? I'll also write that on the left here, right? Our n is equal 5, right? That makes sense. Our order of the polynomial is going to be 1, okay? And then our degrees of freedom was defined as n minus n plus 1, right? That means that our degrees of freedom is going to be 3, right? That's pretty easy. And then and we want the confidence interval at 95 percentile, right? And since our degrees of freedom is 3, so my t value is going to be 395. If I look at table 4.4, I think it's in your first or second lecture. You can check it from there. And that value is going to be, so it's written here, is going to be 3.182, okay? And that's pretty much it for what we need to calculate. And based on that, let's do an XY curve to do a linear regression. Okay, what I do is that I will want to create an XY curve. So to do that, I will have to say create an XY scatter, right, with all points. Okay, I'm going to select my data. My x values, right, are going to be 1 to 5 right there, and my y value is going to be again the corresponding values, right, and this is my LVDT measurement, okay, and that's my experimental. Okay, then I'm gonna press OK, and those are the 5 points that I have. Okay, so you can also measure and put in some information here, right? Because that's not clear what my y-axis and my x-axis is, right? So you can add an axis title here. That's going to be a displacement, right? And that's going to be in let's move to the left a little bit. It's going to be in centimeters, correct? And my y-axis is going to be the LVDT output, right? And that's going to be in volts. Okay. So the only thing that you do here is that you right-click to your curve, and then you can say add a trend line. And once you do, it's going to give you a bunch of options, right? So you can do exponential, linear, polynomial of certain order, right? But we know that it's a linear relationship, so it's basically going to show you your curve right there, okay? And then you can also say show my equation, right? And also show the r square value, okay? So you do that, and what happens is that here's your polynomial, right? So since our polynomial was first order, so our yc is going to be a0 plus a1 times x, okay? So the a0 in this case was 1.04, right? Which I see here, right there. And then my, I'm sorry, my a0 was the other one. It inverts it in there. So my a0 was 0.02, and my ax, a1, is going to be 1.04 times x, okay? And our r square was 993, right? So that means that it is a good fit. Okay, you can say that because my r square was 0.993, so that's a good fit. Okay, and then what I need to do now is to calculate the yc at each point. Okay, what that means is that I basically put in the same polynomial that I read from here, so it will be 104 times x for 1, 2, 3, and 4, and 5, plus 0.02. Okay, so this is the real experimental values, and these are, okay, the polynomial values that we have found. So what we're trying to find is to find the delta, the difference between the two. Okay, and to do that, first we are going to go and calculate the standard the difference. Okay, the difference was, okay, at each point, so let's see, equal to, okay, the y, which is the real value, minus the polynomial value in that point, right, and squared. Okay, there you go. So that's my difference, and these are the differences for all 5 points. Okay, easy. And what was my standard deviation? So if you go back to the notes or the lecture that we do, right, let's figure out where the syx was, right? Syx then, right, was defined as, okay, the difference, okay, by d, so right there, right, so it will be the difference, okay, let's write it down here so that will be easier for everyone to remember. D, right, was defined as sum of I1 to n, right, yi minus yc squared. Okay, we have already completed that term, right? And then the syx, right, was defined as, right, the d, right, divided by degrees of freedom, right, and square root. Okay, so in that case, let's calculate our D first. Okay, our D is going to be, let's calculate D is here, is the sum of all these, right? Okay, and then I will make a different color so that it shows up. So that's my D, okay? And then for this one, I will say this is going to be in square root, okay? D divided by my degrees of freedom, okay? And there you go. So that's the standard deviation that I have. We've calculated as 0.15, 16 almost, right? So we can say 0.16. Okay, so I know my t-value, right? T-value is calculated as, let's go back to here, 3118, right? 3182, sorry, 3 times 182. And then the error is then, right, if you remember, right, it's going to be T395, right, times SYX, okay? And in that case, I'll just going to be doing this times that. There you go. This is my error. Okay, times that, right? And also, this is going to have to be divided by, right? Okay. And then, if you remember, my error was defined as, our error was defined as T395, right, times SYX divided by square root of n, okay, at, in this case, that will be 95 percentile. Okay, and to do that, it will be 3.182, right, times my SYX, that will be 0.0, I'm sorry, 0.16 roughly, right, divided by square root of 5, right, because our n was 5, okay, so that value in Excel, let's go back, it's going to be this times that divided by square root of n. Okay, so then my error, right, is then 0.2265, and we can roll that to roughly 0.23. Okay, so what this means is that the my confidence interval, right, is at any given point, right, is YC, right, plus minus 0.23 at 95 percentile. Here's my confidence interval. Okay, hopefully this was good. So the one way that you can show this confidence interval in graph, right, is that the you can do YC value, right, which was here, 1.06, right, minus the error value, right, and you can do this for each one of them, not the last one probably, and then you can do the same thing for that, but instead of minus you can do plus. Okay, so that will be your error band. Mistake here. This is not that. That's going to be this. There you go. And if I propagate that, okay. So I can plot them as new data, right? So that's going to be add yc plus error, right? The x value is going to be the same, and then the y values are going to be, what did we do? This was the plus error, right? So then I can do the plus error here. Okay, done. And then I add another one, yc minus error, and then that will be the same xy values right there, and then the y values will be here. Okay, let's make it a little bit more visually appealing. So I'm going to say show a line, solid line, right? But give it dash type, okay, and make the color say orange, you know, and then the markers options, no markers, right? And go to the other one, and then we'll say no markers, line will be solid line. Let's make it orange as well, why not? And then we give it some type like that. Okay, so in that case you can plot this here, right? So there you go. So here's your curve that you've generated, right? And here's your main line fit, which is the blue, and then you have your experimental points as blue, and then you have your error band, which is the one that you're calculating. So basically what this is saying is that within this error band, your polynomial can represent your experimental data. Okay, and I'm also posting the same thing, the lecture notes as well, and you can follow that from there. Thank you.